Okay, let's learn about sampling distributions and the central limit theorem. Section 7.1 in introduction, there's definition 7.1. A statistic is a function of the observed random variable in a sample and known constant. So a statistic is used to inference about the population. Some example of a statistic is described in this example. So the sample mean y bar or the sample variance S square, minimum of y, y1, and the maximum of y, and the sample mean and so on. They are example of a statistic, and they are all derived to describe the population. Okay. Okay, let's move on to example 7.1. A balanced die is tossed 3 times. Let y1, y2, and y3 denote the number of spots observed on the upper face for tosses 1, 2, and 3 respectively. Suppose we are interested in y bar, the average number of spots observed in a sample of size 3. What are the mean mu y bar and standard deviation of y bar? And how can we find the sampling distribution of y bar? Okay, so the first problem is we would like to find the mean of y bar, and this is expected value of uh, 3 over y1 plus y2 plus y3, and actually expected value of e of y1 is actually e of y2, and this is actually e of y3. So this notation is 3 over e of y1 and 3, uh, and this is actually e of y1. The expected value for one die, it should be 3.5, because for one die, uh, 1 to 6, and every probability is 1 over 6. And actually, the example 3 point example 3.222 have this example. It calculated e of y is 3.5, and variance of y is 2.9169. Oh, okay. Yeah, it already calculated from previous example 3.22. So let's admit that this is already calculated, and let's move on. And what would be the variance of y bar? Variance of y bar. This is variance of 3 y1 plus y2 plus y3, and from the previous formula, the theorem, it's 9 times 3 variance of y1, and so this is and variance of yi is 2.9167, and so 3 and 9 cancelled, and this part is 3, 2.9167. Okay, and the next question is, how can we find the sampling distribution of y bar? So we want to find the sampling distribution y bar, and actually we can calculate it directly. So in this one, what would be the simple event? So simple event can be described like this. Every die have 1 for their front value, and in this case the result is 3, the 1, the average value of all die toss. And so what would be the table of y bar? Probability of y bar, probability of y bar, And here we have y bar and 1. What are all possible events? The number of all possible events would be 6 to the 3, and we can, the next event is 1 1 2, which is 4 over 3, and 5 over 3, and 2 2 2 dot dot dot. This would be the distribution, sampling distribution for y bar. And for 4 3, it's 1 1 2 1 2 1 2 1 1, so three possible simple events, 3 over 6 to 3. And what about 5 over 3? It's 1 1 2, 1 2 2, and 1 1 3. Or combinations for 1 to 2, or combinations for 1 1 3, they are 6, so 6 over 6 to 3. And similarly, we can calculate the probability for each event. Okay, then, and that would be the sampling distribution for y bar. Okay. And in figure 7.1, it describes the simulated sampling distribution for y bar. So in the example 7.1. So in example 7.1, we calculated the sampling distribution of y bar. And actually in here, what it did is it rolled dice like 4,000 times, and for 4,000 times it calculated value y bar, and then look at the distribution of y bar. And as we know, the y bar can take value from 1 to 6. Y bar is average value from 3 dice, so the value can take from 1 to 6. And as we know that for 1, the related probability would be 1 over 6 to the 3. And also what we know, expected value of y bar is about 3.5, and as we can see, it looks like the expected value from this distribution would be 3.5. So this is the how we can simulate sampling distribution from computer simulation. Okay. Let's move on to Theorem 7.1, which is related to sampling distributions related to the normal distribution. Let y1, y2, and yn be a random sample of size n from a normal distribution with mean mu and variance sigma square. Then y bar is an average value of that n number of normal distribution, is again normally distributed with mean mu and variance sigma square over n. Okay, so y1 to yn, they are normally distributed, and the average value of them also it's also normal with mean mu and variance sigma square divided by n. And how we can prove it? And actually, we can directly apply theorem 6.3 here. So in 6.3 here, in from the U, let AIs as 1 over n. So if AIs are all 1 over n, then this U statistics is exactly y bar. And so the expected value of U, if all AIs are 1 over n, this is and mu1 to mu n are all mu, then this is mu, and also this is sigma square over n. You can directly apply theorem 6.3 to solve this theorem. Okay. Okay, let's move on to example 7.2. A bottling machine can be regulated so that it discharges an average of mu ounces per bottle. It has been observed that the amount of fuel dispensed by the machine is normally distributed within sigma equals 1 ounce, a sample 1 ounce, a sample of n equals 9 filled bottles is randomly selected from the output of the machine on a given day, all bottled with the same machine setting, and the ounces of fill are measured for each. Find the probability that the sample mean will be within zero point 0.3 ounce of the true mean mu for the chosen machine setting. So we want to find the probability that the sample mean will be within zero point 0.3 ounce. Okay, let's use blue color. Find the probability of sample mean will be within zero point 0.3 ounce. Minus zero point 0.3, 0.3. So we want to find this probability, and what's the distribution related to here. And we know that the distribution of y bar, it follows normal distribution with mean mu and variance sigma over n, and here sigma is 1.0 and n is 9, so 1 over 9, and so sigma square is 1 over 9, sigma is 1 over 3. And what we know is that if y bar minus mu divide by 1 over 3, it will follow normal distribution with mean 0 and variance 1. So we can use this distribution. So to calculate this probability, the probability of for the inside part, we converted mu divided by 1 over 3, and which is multiplying 3 to every side, which is minus 0.9 and 0.9. And so, and this is normal distribution, standard normal distribution, and what we can do is probability of minus 0.9, standard normal distribution 0.9. Okay, and so this is standard normal. We want to find this thing, and actually this is same as 1 minus 2p probability of z is greater than 0.9. So here the probability of z is greater than 0.9. This is 0.1841, and so you put it this value and you can calculate the value here. Okay. Okay, let's move on to example 7.3. Refer to example 7.2. How many observations should be included in the sample if we wish y bar to be within 0.3 ounce of mu with probability 0.95? Okay, so we want to find probability of 0.95 if we wish to y bar to be within 0.3 ounce of mu. So the probability of actually I already prepared it. Okay, so what we would like to find is probability of y bar to be within 0.3 ounce of mu with probability of 0.95. And what is the related probability distributions? What we know that y bar follows a normal distribution with mean mu, and the variance is sigma over n, sigma square over n, so 1 over n. And from here, what we know is y bar minus mu divided by square root of sigma square 1 over n follows normal distribution with mean 0, variance 1. And actually, we know the distribution function of this, the standard normal distribution. So, and also what we know is for this standard normal distribution, we know that probability of the standard normal distribution z, absolute value of z, is less than or equal to 1.96. It is 0.95. We know this, so we will use this to solve it. Okay, so from here we can represent this part this way. P we multiply square root of n to all sides, so minus square root n times 0.3 square root of n y bar minus mu and 0.3 square root of n. This is 0.95, and this is actually z. And so what we know is this number is 1.96, and this is minus 1.96. Okay, so we can solve it to calculate square root of n. N 0.3 square root of n equals 1.96. So 1.96 divided by 0.3 square is n. And if you calculate this number, this is 42.68. Okay, so using this, you can calculate the sample size. Let's move on to Theorem 7.2. Let y1, y2, and yn be defined as in Theorem 7.1. Then zi, y1 to yn be defined in Theorem 7.1, which is y1 to yn are normally distributed with mean mu and variance sigma square. So if this is the case, then if we define zi as yi minus mu divided by sigma, then this follows normal distribution. They are independent standard normal random variables, and I is 1 to n, and so this is sum of zi squares, and zi squares, each of zi squares follows chi-square distribution with degrees of freedom 1, and this is sum of n number of chi-square. So this is chi-square distribution with n degrees of freedom. This can be directly proved by applying Theorem 6.4. Okay. Now let's move on to Theorem 7.3. Let y1 to yn be a random sample from a normal distribution with mean mu and variance sigma square. Then this term, n minus 1 times s square divided by sigma square, which is this term, and has chi-square distribution with n minus 1 degrees of freedom. Also, y bar and s square are independent random variables. Okay, so actually I'm going to skip the detailed proof for this Theorem 7.3 because this is very kind of long, and if you are very interested in proving this theorem, refer to this YouTube lecture. This is actually my previous lecture in Mathematical Statistics 1. And from here, I would like to describe some key points or key ideas to prove this theorem, and actually that is described here. Suppose y1 to yn is a random sample from a normal distribution with mean mu and variance sigma square, and the next thing we need to prove is that y bar is independent of yi minus y bar. If you prove this thing, this is first thing to prove. If you prove this thing, then you represent this term with the sum of these two terms. You can do it, and then from here, this s squared term is the function of yi minus y bar. So this s squared term is a function of yi minus y bar, and this term have function of y bar, and so these two terms are independent, and so using the moment generating function trick, you can actually derive that this part left hand side follows chi-square distribution with n degrees of freedom, and this part, let's this red part follows chi-square with n minus 1 degrees of freedom, and this green part follows chi-square distribution with 1 degrees of freedom. After proving like this, then you can prove that this term, the red term, this follows chi-square distribution with n minus 1 degrees of freedom, and you can also prove that y bar and s square, since s square is a function of yi minus y bar and s square are independent. Okay, actually this is the sketch for the proof for theorem 7.1. If you are interested in proving it more theoretically, check my previous lecture. The link is here. Okay. Okay, suppose y1, y2, and yn is a random sample from a normal distribution with mean mu and variance sigma square. To do the inference about mu, we use y bar. We usually use y bar, and especially we know that y bar minus mu divided by sigma over square root of n. This term follows normal distribution, so we can do some tests related to y bar. However, there is a problem. Most of times, the sigma square term here is unknown. So usually we want to do the inference on this thing. Usually, rather than using sigma square, we estimate sigma square with s and replace sigma with s. And so what we need is the distribution of this term. Then what is the distribution of this term? Here comes the definition 7.2. Let z be a standard normal random variable, and let w be a chi-square distributed random variable with degrees of v degrees of freedom. Then if z and w are independent, if we define our t this way, t is z divided by square root of w divided by v, or nu, I think, is said to have a t distribution with new degrees of freedom. Okay, and here, if you let z as this term, and if you let w as this term, then what you can derive is t is this, and if you put z as here and w as here, then you can derive that our t is this term. This is the previous term that I questioned. What would be the distribution of y bar minus mu divided by s over square root of n? So So now you can answer that question. What is the distribution of this thing? And the distribution of this thing is t distribution with n minus 1 degrees of freedom. Because the W term here, from the previous theorem, we proved that this W term follows chi-square distribution with n minus 1 degrees of freedom. So, so this thing follows t distribution with n minus 1 degrees of freedom. Okay, and figure 7.3 describe the shape of the t distribution. So this is standardized normal distribution, and as we can see, the t distribution have fatter tail. So the tail distribution of t distribution, it is a little fat than standardized normal distribution. And if the degrees of freedom, if the n minus 1, the degrees of freedom goes large, then the t distribution converges to the standardized normal distribution. That's what you should know. And yeah, let's move on. Okay, let's move on to example 7.6. The tensile strength for a type of wire is normally distributed with unknown mean mu and unknown variance sigma square. 6 pieces of wire were randomly selected from a large row yi. The tensile strength for portion I is measured for I equals 1 to 6. The population mean mu and variance sigma square can be estimated by mu, y bar and s square, respectively, because the sigma square for y bar is sigma square divided by n. It follows that sigma square y bar can be estimated by s square over n. Find the approximate probability that y bar will be within 2s divided by square root of n of the true population mean mu. So we want to find the probability of y bar minus mu within 2s divided by square root of n range. 2s divided by square root of n. Okay, we want to estimate this probability, and what we know, actually we previously learned this thing, y bar minus mu divided by rather than sigma, actually rather than sigma over square root of n. Rather than this thing, if we put s here, like s divided by square root of n, then from the previous theorem, we learned that this follows t distribution with degrees of freedom n minus 1. So here n is 6, so degrees of freedom is 5. Okay, so we can convert this probability this way. Probability of minus 2 y bar minus mu divided by s over square root of n. Yeah, then this thing follows t distribution with degrees of freedom 5, and from the table in the appendix table for t distribution, we know this thing. So probably we can say that our approximation of this probability is about 0.9 or something. Okay. And suppose that we want to compare the variance of two normal populations based on information contained in independent random samples from the two populations. Samples of size n1 and n2 are taken from the two populations with variance sigma 1 square and sigma 2 square. Intuitively, s1 square divided by s2 square could be used for the inference about the variance term. So the next question is, what would be the related distribution? Let's check. Okay, so here comes the definition 7.3. Let W1 and W2 be independent chi-square distributed random variables with nu1 and nu2 degrees of freedom respectively. Then F defined this way is said to have an F distribution with nu1 numerator degrees of freedom and nu2 denominator degrees of freedom. Okay, and let's take W1 and W2 from the previous example. So previously we were talking about the population variance, how we can compare population variance of two population. The W1, this can be related from the first population. S1 square is sample variance from the first population, and we know that this W1 follows chi-square distribution with n1 minus 1 degrees of freedom, and this W2 term can be calculated from the second population samples, and we know that this is chi-square distribution with n2 minus 1 degrees of freedom, and since those samples are randomly sampled from each distribution, these two W1 and W2 terms are independent. And from the definition of this F, here W1 and W2 are independent chi-square distributions. And so W1 divided by N1 minus 1 divided by W2 divided by N2 minus 1. This term is actually this thing. You can calculate it by yourself. Then this term, if you cancel n1 minus 1 from here and n2 minus 1 here, you can check that this term is same as this term, and so this term will follow F distribution with degrees of freedom n1 minus 1 and n2 minus 1. So using this F distribution, you can do the inference about the population variance, differences in two population variance. Okay. Oh yeah, this way. Okay. And the figure 7.4 describes the shape of the F probability distribution. Okay. Okay, let's try to solve the exercise problem 7.37. Let y1 to y1 to y5 be a random sample of size 5 from normal population with mean 0 and variance of 1. And let y bar, this is sample mean of yi, actually, of 5 samples, and let Y6 be another independent observation from the sample population. Then the question is, what is the distribution of A, B, and C? The first one, W equals I equals 1 to 5 yi square. And here, what we know is yi, let's use blue color, yi follows normal distribution 0, 1, so standard normal distribution, so yi square follows chi-square distribution with degrees of freedom 1, and the W term is sum of chi-square distributions, and there are 5 number of chi-square distributions, so the W follows chi-square distribution with 5 degrees of freedom. Okay, and let's move on to number B. U equals this thing. What is the distribution of U? And actually, you can write it this way. W equals U plus Y bar. If you write down this, U is this thing plus Y bar, then you can easily check that W can be represented as U plus Y bar. And another finding that you can check is that this U part and this Y bar part, they are independent. they are independent variables. Mm, Actually, the reason is from the proof of the previous theorem. I didn't cover it in this lecture, but you can check it from the my previous lecture from Mathematical Statistics 1 course. And from here you can apply moment generating function technique. So MWT is actually MUT times my bar t, because the definition of moment generating function is expected value of e to the tx tw, and here e to the expected value of tw is u plus y bar, and so here this is expected value of e to tu times e to t y bar. And since the u and y bar are independent, you can write this as e to the expected value of tu times expected value e to t y bar. And here these are moment generating function for u and moment generating function for y bar. So this term is moment generating function for u t and moment generating function for y bar t. And from here, you also know that W follows chi-square distribution with degrees of freedom 5, and you know the moment generating for chi-square distribution is 1 minus 2t to the minus n, which is 5 over 2. Okay, and also the moment generating function for y bar, this one is chi-square 1, and so this one is 1 minus 2t 1 over 2, and so this part, moment generating function for u, this is 1 minus 2t minus 4 over 2. So we can say that this w, the moment generating function for w is this one. So you can say that w follows chi-square distribution with 4 degrees of freedom. Because if you know the moment generating function, then you know the distribution. And also actually you can apply apply the theorem, but anyway, this is how you can prove for B. And the C is easy. For C, you know the first term follows chi-square distribution with degrees of freedom 4, and the last term is another independent chi-square distribution with 1 degrees of freedom. So some of these two will follow chi-square distribution with 5 degrees of freedom. Okay, this is proof for exercise 7.37. Let's move on. The homework for 7.2 are these, 7.10 and 7.15.